Hello everybody. Today's video presentation is about RNN encoder and decoder architecture. Before going there, we will start with a refresher of what are the different types of RNN that we have discussed in the last two videos. And then from there, we will go to the need for encoder decoder architecture. Very quickly about the types of RNN, one to many. Examples were given an item name, generate the description for that item, or given a genre, generate music around that genre. This is, you can understand, is the base for generative AI, where you are giving a small keyword and from there a description is generated. Many to one is the summarize the description of a keyword or classify the sentence into a positive or negative classification. Then many to many, it is the beginning of the sequence of sequence network. There is a one-to-one correspondence between the input and output sequences. As you look at these parts of speech tagger, you can see this sentence, a cat sat on the mat. As each words are coming in the network, the parts of speech are getting tagged. Determiner for A, noun for cat, and verb for sat, and likewise. So that is what we mean when we say there is a one-to-one correspondence between the input word A and output word determiner, input word cat and the output word noun. The second example could be word-to-word translation or named entity recognition. For example, John is starting from New York and reaching to Kempegowda, Bangalore. So network would be able to understand John is a person, New York is a place, Kempegowda Airport or Bangalore. So like that, the name entity recognition helps. When you come to many unequal length, machine translation is a very good example, where given a Hindi language, for example, मैं machine learning पसंद करता हूँ. So around 6 words, but when you speak in English, then it becomes I love machine learning, 4 words. So it's not one-to-one correspondence. Entire sequence is understood and the translation is done. It's not word-by-word translation, right? Speech recognition is another example of this. How do you design such a network when there is unequal input and output length? What we do is summarize the source sentences. For example, the Hindi, what I said, is a 6-word character to a many to one. We already learned about this network. So in T's time step, for example, let's say it is 6. So 6 words are there and then they are converted into one hidden state. This we already know from our previous video. Now we create one many to many network, and then there the parameters are different. Where in this network the parameters are shared, obviously within the network only the parameters are shared. Here we are creating a different network, therefore the parameters are different, which are, you can see, indicated by a D, because this is also called decoder. We'll come to that point. So this is how the parameters are different here. The second part to be noted here, that we are using the dense layer after this many to many, and we are not using the dense layer immediately after the many to one, because we want this hidden state to use. Okay. Then the third thing is the different time step, which means if this is T, here it is T dash. In our Hindi to English translation, we said that this is 6 words here. Here it is 4 words. So obviously T and T dash is different. And then the summary information goes to the many to many network hidden state. You remember this initial hidden state H0 from our last video. This H0, which is the initial hidden state, is now used for accepting the hidden state of the source language. And that is often called the summary context or the context. Context coming from the source language given as the initial feedback to the many to many network. And that is how the limitation of unequal length is now gone, because it is summarized and given as a hidden input. Now comes the actual English language here. If it is Hindi to English translation, then we are talking about These are the English sentences which you want to teach the model. And then these are the final output from the model. We already learned about what is autoregression, what is a teacher forcing. You remember all of them, otherwise you go back to the previous video and look at them. The first video and the second video will discuss about it. Okay, so what we are talking about is the context remain fixed here for all the time step, whereas when y is given, we are expecting y2 to come, and then the y2 is fed here as the input, and then we are talking about y3 to come. Likewise, at the tth time step, which is yt, we are always expecting t minus 1 model's own input to be fed into the model along with the input. Okay, so that is what is the autoregression we spoke about. So essentially, if you look at mathematically what has happened is that our task was that we wanted to predict y1 to yt dash, y1 to yt dash, which is this y hat information. We wanted to have this given the x1 to xt words. So this is the target and this is the source, and where t dash is not equal to t. That's the expression which you have to do, or that's the task in hand. In order to do that, because t dash is not equal to t, we have taken help of a probability of next word, which is yt, given all the previous words from our teacher forcing or the autoregression principle in the last video. We want to do this along with a context which is acting as the source sentence. A summary information of the source given and the previous words of the target language also given. What is the next output, next word prediction that we want to do? So that's the mathematical model, right? And then to come here to predict this, we are taking help of the HT here, all the hidden state, which are dependent on the hidden state, previous hidden state, the previous word, which is teacher forcing, you recall, and then the context given. So auto-regressive model along with during the training teacher forcing is in place, and the context given, we want to know what is the next hidden state output. Using this hidden state, we will finally do this probability calculation. That's what is the mathematical model. Now let's go to code and see how we can build such a model using TensorFlow. Necessary libraries all imported here, and we are using this data from this GitHub project, or I think English to German language translation. Okay, so we'll not spend huge time on data building. At later stage in later video, when you go to real life example and move forward from RNN to transformer, then we'll do all the steps in detail. This is the file which I have copied in my local machine, and then this is how the data sets are, which has in English it has got this words here or the sentences here like hi, and the corresponding German words are here. And then in the beginning they are only very little words, at the end they will be little bigger. For example, if you come to the end of this and I have taken the last from the data set, you can see this is a big sentence. As you already know, I don't speak French very well, so I would rather not give a speech in French. So maybe this may be not the German, English to German, but English to French translation. Could be, okay. Okay, this is the French sentence. I will come here later. Couple of things I want to tell you, that there are a lot of functions which again I have taken it from that GitHub project I showed you. They basically does the cleaning of the sentences, does the decoding, splitting of the line, remove the escape characters, punctuation, etc. This is only loading and cleaning part. Then we are doing further cleaning, formatting, and adding some delimiter here. Look at this portion, add delimiter to lines, add delimiter to lines. Do you follow? What it is doing is that with every line at the beginning, it is adding one start of sentence, SOS, and at the end it is adding one EOS, end of sentence. Then after that, the data set looks like this. each of these data set will have the English as a source and the target in French, and they are given as SOS as the start of sentence and ending as the end of sentence. That is why each pair is created. Now, having created this delimited array, we want to tokenize them. Tokenization would mean word will be identified, assigned the index number, which is the numerical number for the word, and then convert this entire sentence as a series of numbers. Very similar to what we had in our first video, where we took a toy example of only 4 sequences, 4 words. They were numbers, right? If you remember, they were all numbers there. The sequences are nothing but numbers. That is what the tokenization and the vectorization will do. Look at this. So we initialize a tokenizer which is provided by TensorFlow. Then within that we are doing the fit on text, which identifies or assigns every word a index number. Basically an array of word, and each word has a index number. Remember our first video where we purposefully had taken a very simple example of only 4 words in a sequence so that you can understand and relate this to here. So this is the fit on text. We'll take the words in a sentence, convert them into a number. That's what we are doing. And here text to sequence will actually perform this job. Once the conversion happens, it will be like this. Each word is represented as a number in that array. There is also opposite to this, which is sequence to text. Given a number, it can convert it to the corresponding number. So that opposite thing is also possible. Now, this will be variable in nature. So some sentences will have 4 words, some sentence will have 10 words. It will take the maximum of it, and then rest of them will be padded with a 0. That's what we are doing when we do pad sequences. And padding is post, which means first the numbers will come, then the remaining portion, which means if something is 4 word, but there is also one sentence which has got 10 words, then for the sentence which have 4 word, 6 number of zeros will be padded, so that all become equal length of 10 words in a sentence, padded with 0. Okay, that's the part which is done. And then the last bit is one hot encoding. Again, in our first video we explained what it means. Here, for example, if it is 2, but the entire word length vector here is let's say 3140 is the length of one vector. Each word has to be represented with 310 number of 0 and 1. Then the 2 will be represented by third index of the array, 0, 1, 2. So the third index will be 1, remaining all of them, which is 3100, 0 and 3, will be filled up with 0. Not a very good option, but that's easiest way to represent word. So that's what we are using here, 2 categorical. It converts them to one hot encoding, and we have purposefully kept it simple, similar to our example in video 1. In reality, we'll take help of something similar to embedding layer to learn the word in a more accurate manner. And at the end of it, we see that the encoder and the decoder now have different sequence length. 101 is the number of words which are present, or the sequences in present, which is in English language. In the target language, which is French or Germany, 76 words is the sequence length. This is T, 101, 76 is the T dash. One more thing which we have to understand is this line. Understand this very carefully, because this will be a trend or the pattern which will follow subsequently when you go to more advanced models as well. See what is happening here, that for the encoder we feed in all the data as is. All the 101 sequences are just fed into this, and then we get the summary. Okay, so that's what you will see here also in the Jupyter notebook. Encoder data, there is no change. We are not doing this adjustment. Encoder data is just the one hot data as is. But for the decoder input data, we are doing this adjustment. What we are saying is that the decoder data is all but the last token. Why so? When decoder input is getting received, and then it is expected to predict the next token. So we are giving y1 and expecting y2 to come. y1 given and y2 is expected to come. Therefore, as we reach to the last stage of tth stage, we don't need to give this one. We have reached to yt minus 1 and we are expecting model to give the output of yt dash, right? Therefore, we don't feed the yt, and that is why the input is all data except the last token. We don't give the yt. On the other hand, this side, label side, if this is the model output, we are comparing everything except the first one, because once we feed in the first one, you are getting the second output. So the first one is not required. Second step onward till the yt, we need that data. And that is the adjustment which we have projected here. We are saying that decoder input data should be all but the last token, yt dash is not provided, and decoder output data should be all but the first token, where yt dash is required but the y1 is not required. Agreed? This is the input and output alignment for the data which would be required even subsequently going forward. This pattern will be followed. End of the data preparation, we got x1 as the encoder input, x2 as the decoder input, and y as the label for comparing and calculating the loss. You see, this is what has happened. 101 sequences, and each vector is of 3140 length. Earlier it was very less, three dots we presented for each vector. You remember in the first video? Now we have taken real life examples, so it has become 3104 is one vector size. Okay. When we do the embedding for word representation, this could be much smaller. So these are the shape of our target data. We have taken 1000 example. 101 is the sequence length of encoder. 310 is the vector for the encoder. 76 is the sequence for the decoder. 4139 is the vector length for the decoder, and so is for the level. So these are again variable which we have extracted from the word, what is the encoder sequence length and decoder sequence length, then forming the encoder just like the way we had done in our first video, initializing the encoder input. But instead of giving a sequence length, this time we could have given the same variable encoder sequence length. We give it none, which automatically adjusts the sequence length. Similarly, for the decoder input also, you can see that we have given the none. So encoder input and decoder input shapes are different as expected from our PPT architecture. How do we connect these two? Encoder's final output has to go to decoder input, right? In the first video also we said that this is important thing to learn. Look at here. When decoder we are initializing, we say decoder inputs, which is the target language which is provided, and the initial state is encoder state. This is what connects you with this is what is connecting final hidden state is going to the initial state of the decoder, implemented through this line. Initial state is equal to encoder state. One more thing, length of the context vector. This is the context vector, C. What is the length of that? What is the size of that vector? That will depend, because the larger it is, it will be able to summarize it better. More information will be there from these sequences. That is what you control through this line, which is RNN units, which will determine what is the size you are getting as the output of the. And we applied one example to check the shapes, and we are finding that yes, really indeed the encoder output state, which is the final state, is a vector which has got 512 elements equivalent to this one. Decoder we already explained. In the encoder we are interested to receive the final state. In the decoder we are interested to receive the decoder all sequence output. So therefore return sequence is made as true and decoder output is what is important for us. Then we are passing it to the decoder dense layer at this line, and then those vectors are converted as a probability using the softmax layer. So you can see that decoder output is a array of probability number, not 0 and 1. Whereas the y, which we will be passing for comparison, the label is a one hot vector, which is 1 and 1. How do you convert this one? One side you are saying output is number probability numbers, and the label is a set of 1 and 0. You have to make it both as 1 and 0. The categorical cross entropy function will automatically convert and calculate the loss. These two lines we have not seen in the previous two video, but it is quite common for any neural network training. So it is basically you are mentioning what optimizer you are using, which is Adam here, loss, and what metrics you are using for calculating the accuracy. So this calculates the loss. In our second video we discussed about the loss function. So this is the loss function, and then once the loss is calculated, Adam is the optimizer which will do the gradient propagation. Fine. Let me know in the comment section that if you want me to create a video explaining this topic. We can actually build them manually and then demonstrate to you how exactly these are calculated and then correlate with our second video. And the fit is the iterative process for fitting the data one by one. In fact, you don't fit one example at a time. You do it through a batch, just the way other deep learning system will work. So here the batch system is 64. When the 64 batches gradient are calculated, in one go the weights are updated, right? Here this is how the training progressed, only for 10 epochs, 15 epochs, and we could see that it could achieve around 75.53% of accuracy. We come back to the PPT. We have this context information for 101 sequences, time steps into one vector. Is it not prone to loss? Obviously. So this HT in most of the time will not be able to give the full information of the source data. And that is why this encoder decoder, this is the vanilla encoder decoder, is not strong enough to do a machine learning language translation. Okay. Apart from other problems which we discussed for RNN, gradient vanishing, the recurrent nature, okay, this is additional problem when you are talking about machine learning translation, that because of unequal length, we are trying to pass the summary information as a context to the decoder, but as a result, the source language information is not properly communicated to the decoder because there is a loss. You are converting the sequence to a summary information as a context. So the context, how do you make the context passed into all this time step is the input and output alignment. Your input sequence length is different from the decoder input length. How do you align these two so that this context captures more information than what we have given in one hidden vector is the topic for the next video. Okay, see you in the next video.